test. Yeah, all right. Thank you for the kind introduction, and thank you for joining. This presentation is based on a master thesis of Mahsa Gheibi. We did this paper together with Philipp Hagedorn, Zinke, and Markus König. And it's about the reuse of bridge components. And we used a semantic web approach for this. Why this is important? Because 85% of the German federal highways are made of concrete, so there's a high potential for circularity and reuse. And we also have to consider about it because of the European waste hierarchy, which clearly says that prevention of waste is the highest goal. After this, there comes the reuse of components. And we have a couple of opportunities with that. For example, we have limited disruptions to nearby operations. We can minimize waste and preserve natural resources. We can reduce landfill and saving energy. And we also potentially can reduce emissions and pollutions. So our goal is the reuse of building elements, especially of concrete elements. And we have an approach for that we want to use data we already have. So inspection data, which is defined in the German guideline for preservation of bridges, and also in a German DIN norm about bridge inspection. And there's also one case study we used for our work by Nazemi et al. And yeah, the challenge here when we want to reuse bridge components is how to evaluate which components are reusable and which not. So our overall research question is, how can a rule-based system reliably assess the reuse potential of bridges, considering data completeness and the required parameters? And we followed this methodology to do so. So first we have the assessment parameters coming from the bridge inspection, and we fill them in a BIM model. After this, we can check the model for completeness with IDS, the information delivery specifications by building smart. And we need to convert the model into an RDF graph representation of this model because we want to perform shackle shapes. So we want to search in this graph model which components are reusable, defined on our rule-based system. We have a couple of proposed parameters for that. First, we have the damage class. You can see it in the small table at the side. There are a couple of damage class scores we use. Then second, we have the use classes, which rely on exposition classes for concrete and steel, and also on the failure consequences of components. And these come also from DIN norms and from a work from Bertola et al. And then third, we have the element type. So is it cast in situ or is it a prefabricated element? And we also have information about the deconstruction process, so about the connections and the accessibility of the elements. And just keep that colorization a few seconds in mind for the next slide. So here we have that 4 groups of parameters, and they come together in our framework, which consists on 2 main parts. First, the reuse grading table, which includes the damage class and the use class. And second, the disassemblability score, which includes the element type and the deconstruction information. As you can see on the right, there are some assigned values. We can fill in this equation. And yeah, we implemented this looking like that. Here you can see a code snippet. So our rules are, first, the reuse grade must be 1 or 2 coming from that table. And our second rule is that the equation, the disassemblability score, has to be minimum 0.7. And yeah, that implementation you can see on the right is based on semantic web technologies. So yeah, as I said, we used linked data and the RDF graph representation of our model to perform that shackle shapes to query or to search in the model for reusable components. Yeah, to get an automated assessment. So we search in the whole graph for reusable components. We did a case study to test this approach with a real-world IFC4 model of a bridge from our industry partner, HOCHTIEF. And yeah, in that workflow, as I said, we first enriched the model with our inspection data. We were able to check the completeness of that inspection data in the model. Then we needed to convert it to an RDF graph. And during this process, we needed Sparkle construct queries to get our 4 parameters. For example, here you can see the use class. We had to generate it based on our parameters we collect in the inspection. So you can see here, it's relying on the structural functionality and the exposition class of the concrete and of the steel, for example. Yeah, and thereby we received the automated reusability check with the shackle shapes. Here you can see an example of this, of one shackle shape. And in the middle, at the bottom in the table, you can see the assigned reuse grades of different elements of the bridge. Yeah, to give a proof of concept of this whole framework, we performed the case study as shown. We did it with synthetic data, and unfortunately, no components in this case study met the criteria because the disassemblability scores were low. But to check the whole framework for plausibility, we did a small sensitivity analysis of the whole approach, and as you can see here, of the equation. So we filled in the assigned scores for the element type, the accessibility, and the connection type, and tested it out. Yeah, to come to a conclusion, we presented a rule-based framework for the reusability assessment of bridges, bridge components, and we used inspection data and BIM for that. So we have a formalized reuse assessment framework with semantic web technologies. Yeah, we were also able to check the models for completeness, and we support early stage reuse assessments. Of course, this study has a couple of limitations. So our case study was based on synthetic data, and we've not automated the integration of inspection data in our IFC model yet. And the whole reuse of bridge component is also limited by the current bridge design and, of course, the quality of inspection data. So in future, we want to extend our framework with the aspects of recovery, recycling, and disposal. We want to automate the data integration of inspection data in our model. We can do further validation of the parameter widening of the disassemblability score. And of course, we want to apply it on real-world data. Yeah, here are some funding informations. And yeah, thank you for your attention. And I'm here for your questions.
Thank you, Lukas. Okay.